All right, GCSE chemistry time. Let's get going. We're diving right into paper two and how quickly these reactions happen and where they find their balance. It's reaction time.
Yeah, it's all about change, really. And this time, we're focusing on two big ideas. First, the rate of reaction, which is basically how fast your reactants are turning into products and what things can speed it up or slow it down. And then we've got reversible reactions, where it's not just a one-way street, it's a bit more back and forth, like a chemical roundabout going forward and backward, reaching this thing called dynamic equilibrium.
Okay, I like that. Chemical roundabout. So it's a bit like making a cuppa, right? The rate of reaction would be how fast the tea leaves infuse into the hot water. Some reactions are like that sugar dissolving, it's done. But imagine getting the tea back into the tea bag and the water clear again. That's what we're talking about with these reversible reactions and equilibrium. So how do we measure this rate of reaction thing?
Well, we're looking at how quickly a reactant gets used up or how quickly a product forms. It's all about change over time.
So if it's a fast reaction, you'd see a big drop in the reactants or a big jump in the product quickly.
Exactly. And we can measure these changes in a few ways. We might use mass, measured in grams, or if we're dealing with gases, maybe volume in cubic centimeters. We can even get into moles, which is another way to measure the amounts involved.
Right. Moles always got to have those in chemistry. So we could be talking grams per second or cubic centimeters per second. Basically, how much of something changes each second.
Absolutely. Grams per second, centimeter per second, even moles per second, all ways to express the rate. But to really picture what's going on, graphs can be super helpful.
Graphs, scientist's best friend. What kind of graphs are we looking at here?
We can plot the amount of a reaction or product over time. So as the reaction happens, you see the reactant line going down because it's getting used up, or the product line going up as more of it is made.
Right, so time along the bottom and the amount of stuff up the side. So is a steep line a fast reaction?
You got it. The steeper the curve, the faster the reaction at that point in time. If the line goes flat, it means the reaction slowed down a lot or even stopped.
So if the reactant line plummets at the beginning, it means the reaction went crazy fast at the start.
Exactly. Now, if you want to know the rate at a very specific time, you can draw a tangent to the curve at that point.
A tangent, that's a straight line that just touches the curve at one point, right?
Exactly. And the slope or gradient of that tangent tells you the rate of reaction at that exact moment.
Got it. Steeper tangent, faster rate. So what are the things that can actually change how fast these reactions go?
Well, there are a few key players: concentration, pressure, surface area, temperature, and catalysts. It's like a team effort.
Okay, let's break them down one by one. First up, concentration. How does having more or less of something affect the reaction speed?
Imagine a party in a room. If there are only a few people, they might not bump into each other that often. But if you cram the room full of people, well, they're going to bump into each other much more.
A very lively party.
Right. It's the same with reactants in a solution. More reactants crammed in, more collisions, faster reaction.
Makes sense. What about pressure? Does squashing things together make them react faster?
Pressure mainly affects reactions with gases. Imagine a balloon. If you squeeze it, the air molecules inside get closer together and collide more often.
Oh, like squashing more air into a football. The air molecules hit each other and the inside of the ball more often. So higher pressure, more collisions, faster reaction.
Exactly. Now let's talk about surface area. This is more about solids.
All right. Solid ground, how does that work?
Imagine a big block of cheese versus grated cheese. Which one melts faster?
Grated cheese, for sure.
Exactly. That's surface area in action. With grated cheese, you have more surface exposed, more contact with the heat, so it melts faster. It's the same with reactants. Breaking a solid into smaller bits means more surface area, more contact with other reactants, faster reaction.
That's why sugar dissolves faster than a sugar cube.
Exactly. And now, the big one, temperature. Heat things up, things happen faster, right?
Yeah, like heating up that pan to melt the cheese.
Exactly. When you heat things up, you give those molecules more energy, they zoom around faster, crash into each other more often, and with more force.
So they're not just bumping into each other more, they're hitting harder.
Yeah. More energy, more successful reactions, faster rate. And finally, we have the mysterious catalysts.
Catalysts, they sound a bit magical.
They are pretty amazing. Catalysts are substances that speed up reactions, but they don't get used up themselves. They're like the helpful friend who sets up the date but doesn't actually go on it.
So they're like matchmakers for the reactants, speeding up the reaction without being part of the final product.
Exactly. Enzymes are a great example. They're biological catalysts that make loads of important reactions in our bodies happen quickly.
So how do these matchmakers actually work?
It comes down to this idea of activation energy. Think of it as a hill that those reactant molecules need to climb to react.
Right, so like an energy barrier.
Exactly. Now, concentration, pressure, surface area, they all increase the number of times those molecules try to climb the hill, and temperature gives them more energy for the climb. But a catalyst lowers the hill.
Oh. So it's like digging a tunnel through the hill instead of making the molecules climb it.
You got it. Catalysts provide a different path, a lower energy path, making it easier for the reactants to react. More successful climbs, faster reaction.
Okay, I think I'm getting the hang of reaction rates. Now, what about those two-way reactions, the reversible ones?
Ah, yes. Reversible reactions. They're like a chemical dance where partners can swap back and forth. The products can react to make the original reactants again.
So it's not just A plus B makes C. It could be C breaking back down into A and B again.
Exactly. We use a double arrow to show it can go both ways, and sometimes, by changing things like temperature, we can nudge the reaction in the direction we want.
Like the Haber process you mentioned earlier. What's that all about?
The Haber process is how we make ammonia, which is super important for fertilizers. We take nitrogen from the air and react it with hydrogen to make ammonia. But the reaction is reversible. The ammonia can break back down into nitrogen and hydrogen, so it's N arrow plus 3 H arrows to an H arrow.
Okay, so that double arrow means it can go both ways.
Yeah.
What about energy in these reversible reactions? Does that change too?
Well, if the forward reaction releases energy, making it exothermic, the reverse reaction will absorb that same amount of energy, making it endothermic. It's like a perfect energy balance.
So it takes energy to break ammonia apart, but making ammonia releases energy.
Exactly. Now, imagine you've got this reversible reaction happening in a closed container, like a sealed bottle. Nothing can escape.
Right, trapped reactants and products.
Right. In that closed system, things will eventually settle into a state of dynamic equilibrium.
Dynamic equilibrium, that sounds intense. What does it
Yeah.
actually...
Imagine a two-lane road with equal traffic flowing in both directions. The number of cars going each way stays the same. That's what happens at equilibrium. The forward and reverse reactions are still happening, but at exactly the same rate.
So it's not that the reaction stops, it's just that both directions are perfectly balanced.
Exactly. It doesn't mean the amounts of reactants and products are equal, just that they stay constant because they're being made and unmade at the same rate. It's a dynamic balance.
So it's like a busy train station, people constantly coming and going, but the overall number stays the same. What happens if we try to mess with this equilibrium?
Well, then we get to Le Chatelier's principle. This principle says if you change the conditions of a system at equilibrium, the system will shift to try and undo that change. It's like a tug of war, always trying to maintain balance.
So it's like a seesaw that tries to level itself out again after someone sits on one side.
That's a great way to put it. Let's say we increase the concentration of a reactant. What do you think will happen?
If there's more reactant suddenly, it seems like the forward reaction would speed up to use up that extra reactant. So the equilibrium would shift towards making more product, right?
Spot on. And if you add more product, the equilibrium shifts back towards the reactants to use up the extra product you added. It's always trying to balance things out.
So it's a bit like adding more weight to one side of that seesaw. The other side has to adjust to compensate. What happens when you change the temperature?
Temperature affects whether the endothermic or exothermic direction is favored. Remember, in reversible reactions, one direction releases energy, exothermic, and the other absorbs energy, endothermic. If we heat things up, the system tries to cool down, so the equilibrium shifts towards the endothermic reaction, the one that absorbs heat.
So if making ammonia in the Haber process is exothermic, heating the system up would actually shift the equilibrium the other way and you get less ammonia.
Exactly. And if you cool things down, the equilibrium shifts towards the exothermic reaction to release some heat and warm things back up.
Clever system. So you might not always want to heat things up, even if it makes the reaction faster initially, because it could mean you end up with less of what you want. What about pressure?
Pressure is a bit trickier. It really matters when gases are involved. You have to look at the balanced equation and see how many moles of gas are on each side. If you increase the pressure, the equilibrium shifts to the side with fewer gas molecules to try to reduce the pressure.
Okay, so in the Haber process, N euro plus 3H, 2NH, you have 4 moles of gas on the left and 2 on the right. Increasing the pressure would shift the equilibrium to the right towards making more ammonia because that side has fewer gas molecules.
Exactly. And decreasing the pressure would favor the side with more gas molecules.
So there's a real strategy to getting the right balance, literally, by tweaking the conditions, the concentrations, the temperature, the pressure to get the products you want.
Precisely. Understanding this balance, this dynamic equilibrium, and how fast these reactions go is crucial for so much of chemistry. Think about the reactions happening inside you right now, or the industrial processes that make so many of the things we use every day.
Wow. It's mind-blowing to think of all those reactions happening all the time, some lightning fast and some super slow, all finding this balance. But here's a thought. What if you have a reaction that's reversible but also really, really slow? How do you get a good amount of product in a reasonable time?
Now, that's a question to keep you thinking. It highlights how the rate and the extent of chemical change are linked. That's the beauty of chemistry, always more to explore.
Absolutely. Keep those reactions bubbling. Thanks for listening.